Alright, here we're going to look at the block diagram for this PI controller system. And we're going to look at how we are able to use the Laplace domains we've talked about before actually functioning within our systems. So we're going to look at how signals flow in the system. So we have some disturbance, how that flows within our PI system as well as our set point, and how this whole system works together. Before we've kind of talked about how the system worked physically, and now we've talked about kind of flow of signals very briefly earlier. Now we're going to talk about this actually physically, like we're actually going to interpret how these signals flow and how they relate to each other, especially with these gains. We've talked about gain in terms of our PI controller a number of times. What error leads to what degree of output. We're going to actually put this to the test now where we're able to calculate, for example, we'll do it together. First, what the analytic change for a disturbance would cause within the system, and then what the we'll do it together as well, how a set point change would affect the system. So let's go ahead. I'm just going to write those two. So delta disturbance, and how that will affect T1, and then we're also going to look at delta set point and how that will affect T1 over time. So let's go ahead and let's discuss this system now very briefly. I've gone ahead and just drawn out a few things. Here we have our system. I'll zoom out just a little bit. We have a disturbance from temperature 2. We have our temperature 1 down here. If this is a set point, we can start here. We'll compare it with the actual temperature here, and we'll get some difference, some error. That will go into our PI controller, and our PI controller will determine some output, some heater setting that should happen. It then goes to our process. I hope as we look at this, these terms look rather familiar. We've talked about modeling our process enough that I'd hope that these terms will look like what you've seen before. We have our K of our process, our dead time, and right here is our process time. So hopefully these things are coming together now. For example, we see this disturbance is just 1/3 of the, it makes sense, the disturbance would have less of an effect on the system, but it will have an effect on the system. And the time that it would take would be rather similar. It depends on the heat capacity of the system more than anything else. So the process takes a heater setting, and what it determines is the delta T. Same thing with the disturbance. Some heater setting goes into the disturbance, or actually rather than some heater setting, we could say some temperature at temperature 2 is different, so that could be a delta temperature, or it could be a Q, whatever you want for this disturbance. But this right here converts whatever is on the left into as well some delta T within T1. Both of these are then added together, and we get our new T1, which comes around and we compare for the set point at the next interval. The key thing I think always as we think about these systems, as we think about chemical engineering, we have lots of balances where we say, this many kilograms is this many moles, things like that. These are the same thing. What's going on here? We talk about these gains, and there you go. We talk about these gains, and really I think this is the key concept right here. Some gain I is equal to, it converts, the gain is equal to out over in. Another way to think about it is whatever in times gain is equal to out. And so some way to, for example, the gain of the PI controller will help us convert from the error to the heater setting, and vice versa. So let's go ahead, let's look really quick at what the gain equations are, and then let's go ahead and define our system. And then, as we said before, we'll look at how a disturbance would affect the system. And then for your assignment, we'll look at how the analytic solution to a temperature set point change. And then we'll obviously validate them with the temperature control lab. Really briefly, we have a couple different gains within our system. We have a PI controller gain. What goes into the PI controller? Well, the error signal. What goes out? The heater value. We talked about that a couple times. So the gain is Kc, K of the gain of the controller, times tau I s plus 1 over tau I s. Process transfer function. What goes into the process? Well, let's think about our temperature control lab. What goes in is the heater setting. What goes out? Change in temperature. And again, those constants should look pretty familiar. What happens with our disturbance transfer function? Well, we have some disturbance, and that results in a change in temperature of our process variable. So here we have that transfer constant as well. Let's now define our variables as far as these e's. Let's think. We'll want to define e. We'll define q1, probably t1 as well, and maybe we'll just leave it at that. We'll see how we're doing as far as if we're able to explain our system. So let's start with error. We'll go ahead to we'll do blue still. Error as a function of s is equal to the difference between temperature set point and T1. And those are functions of s as well. We're in the Laplace domain. Let's move on then. What is Q1 a function of? Well, the way I first think about it is what we were talking about before. That's going to be E S times the gain of the controller, so GC S. Well, we can take that a step further and also say GC S and then expand from up top T set point S minus T1 S. Okay, now what is T1? This right here. Well, we're going to do the same process we did before. T1 S is equal to gain of the process S times Q1 S. That is equal to gain of the process S times gain of the controller S. In fact, you know what? I'm going to take advantage of having an iPad. This is Q1. Copy, paste. So gain of the process and gain of the controller times the error. You can see these are multiplicative. They're multiplying together. That's going to be important. But we also have our disturbance. So this is we'll say T1 I, and this is T1 I. So T1 I is equal to that. T1 I is equal to the gain of the disturbance S times the disturbance. So we'll just say T2 S. So T1 is actually equal to the sum of the two. And again, I'm just going to take advantage of having an iPad. And we didn't need some of that. This, how can I say? Doing these first may seem like a waste of time, but it helps you keep everything neat and organized so that as you do the math, you already have it. And so you don't need to worry about doing it all over again. So I highly endorse it. So there we go, we have T1. In this case, our set point is going to, these are in terms of our deviation variables. So let's think things through for a minute. If we want to know how a disturbance, or how a change in temperature 2 would affect, let me just switch colors. We have temperature 2 go up by 20 degrees, and we're going, that's a horrible arrow. We're going to ask ourselves, what's going to happen to temperature 1 over time? Or over S, either one. So what's going to happen to temperature 1? So to do that, what we're going to do is we're going to think about our block diagrams for a second. We're going to have T2 times some block is going to equal T1. And so what we really need is T1 over T2 within our system. So we have T1. Now what we need to do is get T2, an equation for T2. Let's first simplify T1, and then we'll solve for T2 rather. So let's go ahead and gather all of our, I like highlighting things, and so we'll just highlight our T1s. Think about what that means. Here's T1. Let's highlight our T2s too. Here's T2. And we have our T set point. Let's do our set point in red, I guess. All right. We'll assume that there's no change in set point, and so because of that, TSP can go to 0. So that leaves us with GP times GC times negative T1S plus GD times T2. We'll go ahead, we'll just write that. We're not getting charged per page on this. Put the negative out front. T1S plus GDS T2S. Now, if we want to get this in terms of T1, the best way to do that I can think of is to take all of it, and so I'm just going to go ahead and copy, paste. We're going to add it over. So then T1S multiplied by 1 plus GPS GCS is equal to GDS T2. Now what we wanted was T1 over T2, and so you can see we're pretty close actually. So T1 S over T2 S is equal to GD over 1 plus GPS GCS. So it's like a checkpoint, if you will. Now we know what our GD, our GP, and our GC are. So we're going to go ahead and plug those gains in. T1 over T2 is equal to, go ahead and we'll just scroll up a bit. Actually, I remember them. We'll just write them out. Have this right here, because I can't remember that though. GD is 0.3 over 180S plus 1. This line was too long. E to the negative 15s. Working with these constants all day, it comes in handy. 1 plus GP. GP is the process. If we remember, that's going to be 0.9 over 180s plus 1 e to the negative 15s. This is all multiplied by our controller constants, which are tau I s plus 1 over tau I s, and that's also times e to the negative 15s. Is it? Let me check. Nope, No 15s, but there's a Kc. Okay, now this can look a little bit intimidating. So we've got to figure out how we get this into a form that we like. Let me just pull it out. I'm going to make it a little bigger. Make that a 15 again. All right, let's think about things. We can linearize some things. We've got this 1 plus 15, 1 e to the negative 15s is the main thing. Everything else we can kind of transform from Laplace back. So the way we would do this is we'd do like a Taylor series approximation. Or some other linearization. We talked about linearization before. The whole concept is that at close ranges, we can find the value of a system fairly easily just by taking the value of it and its derivatives. So e to the negative 15s, if we think about that, a Taylor series approximation is going to be, it's of the form where you do, let's see, f of x is roughly equal to the value f at x is equal to 0 plus f prime at x is equal to 0 times the distance we have from that x0 plus f double prime delta x0 over, let's see, is the second derivative? Yeah, it's over 2. And then after that, it keeps on going up. But let's just focus on the first two terms here. So e to the negative 15, if we think about it, and we'll center it around the x. Let's just think about e to the x first real quick. That's going to be e to the x centered around 0. That's going to be equal to 1 plus the derivative of e to the x, which is x. So we have, and let's just focus on that. So some linearized approximation for e to the negative 15s would be 1 over 15s plus 1. Here's that 15s plus 1, and because it was negative, we're going to put it on the denominator. So that's one way we would find the Taylor series approximation. We'll actually do that in MATLAB, and we'll go ahead and do that right now. All right, let's go through this code now. I'll drag this over just a bit. We have the information we discussed before as far as our system. We have our block diagram algebra here, what we discussed before. And here we have our transfer function. You'll notice as we discussed too, there's two ways for us to approximate this time delay polynomial. That's a nice thing about these linearizations. We talked about them earlier in class, and we'll use them for times like this, where these series could go on infinitely, and instead we just take a close approximation, and it's good enough for what we're doing in all practicality. So let's look now at the analytic response to the 20-degree Celsius disturbance. So here we have that analytic form we derived before, and then we have this right here, which is our solution. So let's figure out how we actually did that with MATLAB. MATLAB, one of the best things about MATLAB is their symbolic math. So here we declare symbolic variables s, t, x, y, and z. We define our input 2 as 20 over s, which is our step, times exponent to the negative s, which is our delay, that initial change. Then we have our gains. Kc is 2, tau I is 180, Gc, which is the gain of the controller, is Kc times tau I times s plus 1 over tau is. This is the main thing that isn't just what we had before. we add in our delay. I should say this is just part of the step change. This is our delay, which is 1 over 15 times s plus 1. Our Taylor series approximation of the delay. You can see that right here. So we'll continue now. To create the closed loop response, we have the disturbance gain over 1 plus the product of all loop gains. So that's gain of disturbance over 1 plus GC times GP. Temperature 1 response is the gain times T2. Remember, gain is T1 over T2, so that's how we convert it. You'll notice on the right-hand side, we have each of these actually calculated in symbolic math rather than numerically. So we keep on going. Once we go to these right here, we're going to do an inverse Laplace with the I Laplace function, where we take the equation, T1 for example, and we replace S from the Laplace domain S to the time domain T. And we do the same thing for T2. Finally, we have our our T underscore, which provides the numerical values for each of the places within the first 10-minute interval. And then T1 plot and T2 plot, we substitute in this array. And it would do it analytically still, except for we say instead of some sort of symbolic solution, we want it in the form of a double, which is a float or it's a decimal answer. And so if we look at our plot now, you'll see we go up 20 degrees on T2, and we have an initial rise in temperature for T1, and it comes back down. I should note that both of these are relative to our disturbance temperature. So we could actually go like this. Let's say it started at 23. We could just go plus 23 to both of those and run this section again. You'd see it at the actual temperature rather than, oh, we got to change x. These are x coordinates, these are our y coordinates. So we got to change these to 23 too. Oh, and our y limit is -2 to 22. Instead, let's set that from 20 to, let's say, 45. Hey, there we go. So our T2 goes up, and our T1 has an initial rise, and then it falls back down. Now we're going to discuss our assignment. We'll just go ahead and do that similarly, where I'll have the solution off to the right-hand side as well as the code already written, and let's just discuss it. So we have our gain. We've calculated our gain before. Actually, let's discuss this. I think, so our gain for this process is going to be, we're going to go from, let me get out my pen. Either way, we're going to get to this form right here where it's T1 over T set point. And so let's go, let's come up here and just look at our equations here for a second. A little bit further down, right here. We're trying to get this in the form T1 over TSP. So let's go ahead, let's write that. Get out my pen, we'll just do it all here. T1 over TSP. So let's look at this equation right here, because we've got a T1 and a TSP. The first thing right off the bat is we know that our T2 isn't doing anything. We're not changing T2, so that's going to go to 0. Then we, like before, we have a T1 on both sides. We have this T1, and we have this T1. When we add it over to the right-hand side, we'll get 1 plus TSP Yep, because that's going to be, so it's going to be 1 minus, actually. Let's get out the eraser. Oh, I don't have an eraser. That's unfortunate. So we'll go like this. I was going to do it. We'll just write it all out. So T1 is equal to GC, GP, TSP, minus t1. We move that over, so it's going to be t1, and factoring everything else out. It's going to be t1 plus 1 plus GC GP. And if you can imagine, what we're doing is we're distributing these portions out into both these. So we have GC, and so that's equal to GC GP TSP. So hopefully that makes sense. And then we have these portions right here because we have the negative T1 times GC times GP, and we add that over to the right-hand side, factor out the T1. So then T1 over TSP, we take this and we go here, and we take this and we put it over here in the denominator, and so it's going to be T1 over TSP is equal to GC GP over 1 plus GC GP. So that's going to be our gain of this process. We're going to have our T1 response is going to be this right here times the change in set point. And then we'll obviously convert from the Laplace domain back. So let's now look at our system. Here we have our gain. That's of the other one, excuse me. Here we gain GC times GP over 1 plus GC times GP. And that's going to be a very common theme. If we have the full loop, it's going to be 1 plus it. And up top, it's going to change sometimes. But the bottom, quick and easy shortcut is that. Again, we're going to declare our symbolic variables. Our TSP this time is what's going to change by a step change. And then our T1 response is going to be our gain times the step change. We also have our T set point then in the Laplace domain, as well as our T1 in the Laplace domain. And we'll go ahead with our T underscore lin space for the values that we're going to plot. We need 601 values for all those seconds. And finally, we substitute that array in. Here, we're going to substitute it into each of these two symbolic equations, where we're putting the array in, T underscore, for the variable T, and then we're going to evaluate it as a double, as a decimal number. Finally, we're going to run this on our temperature lab control lab to compare. If we have it, it'll be saved as lesson 25 TCLab data.csv. So the first thing we'll try to do is read that, and you can see I've already done that. I read it from the data. Then we have our Kc, our tau I for our system, and we go ahead and we simulate our PI controller here, and we compare the responses in our graph right down here. So you'll notice the air conditioning is really chilly right now. In fact, it's pushing 16 degrees right now for me. So we're starting just below 20 degrees Celsius, but it pops up and it evens out. Now what's our heater doing? It's remaining about constant as we get close, and those red dots are our actual measured data. So we can see it does similar. It's going to rise and it's going to keep on going. So we have some slight differences from our data, but it's pretty amazing that from our mathematical model of this, we still get that close. So that's one reason Laplace transforms are valuable. We go from this discrete domain to Laplace domain and back to time domain, and we're able to model pretty accurately what's going on, and at least have an idea. You know, this is a pretty good rough estimate. And so there we go. That's our system. We'll move on next to state space simulation next.